Welcome back everyone. For today's video, we are going to be taking a look at my paper in the annual ACM Symposium on Theory of Computing 2024. The title of this paper is Learning Shallow Quantum Circuits, and this is joint work with Robert, Michael, Isaac, Anurag, Zeph, and Gerald. So, without further ado, let's jump right into the action. Let me start by saying that here are two fundamental problems in quantum complexity theory and quantum learning theory. The first problem is, given access to an unknown constant depth quantum circuit U on the right-hand side, the goal is to learn a constant depth circuit that is close to U. The second problem is this: given copies of an unknown quantum state, psi, that is prepared by an unknown constant depth circuit U on the right-hand side, the goal is to learn a constant depth circuit that prepares psi. So in this talk, we will show polynomial time algorithms for both problems. The algorithm for the first problem works for general geometry, while for the second problem, the algorithm works on a 2D lattice. In addition, the algorithms in this talk also works when the depth of U increases from constant to polylog n. In this case, the algorithm runs in quasi-polynomial time. Next, I'll discuss some motivation for these problems. One way to think about NISQ computation, which stands for Noisy Intermediate Scale Quantum, is that it can be modeled as shallow quantum circuits. Shallow quantum circuits are simple, but they are still interesting because they can generate probability distributions that are classically hard to simulate. This has motivated a lot of NISQ algorithms, where the key idea behind this algorithm is try to discover a shallow circuit as a solution to an interesting problem, assuming the circuit exists. And indeed, this can be formulated as a learning problem. So, the main challenge in this direction is how to develop efficient learning algorithms. And in this talk, we will discuss two new learning algorithms that probably work in simple settings. And maybe an exciting future direction is that perhaps these algorithms can be used as primitives for new NISQ algorithms. Next, I'll briefly discuss the key challenges behind these problems. So all of the algorithms we see today follows a two-step procedure. Step one is to learn local observables. So we know that this is easy to do using standard techniques such as classical shadows. And we also know that because the unknown quantum circuit is shallow, the local observables actually provide sufficient information to reconstruct the circuit. So really, the challenge is all about step two, which is to efficiently reconstruct a quantum circuit from learned local observables. And hopefully I will convince you that this is a highly non-trivial problem. And the goal of this talk is to demonstrate new and simple techniques to do this. So let's start with learning shallow quantum circuits. So we are given access to this unknown shallow quantum circuit U, shown on the right-hand side, and the goal is to learn a shallow circuit to implement U. So we will see that the algorithm only needs very simple access, which is single qubit random input-output samples, which looks like this, where the inputs are random single qubit stabilizer states, shown in the blue, and the output is measurement in a random Pauli basis. Next, we will discuss this result, which gives a polynomial time algorithm for learning shallow quantum circuits from random input-output samples. So, a particularly important concept in shallow circuits is the light cone. So here is the basic picture, where we have a shallow circuit, and the bottom is the input and the top is the output. If we consider a small region A, then we can see that each input qubit in A only affects the output qubits in the light cone of A, shown as the blue gates. So here is a naive thought. if we can somehow undo the blue gates by applying their inverse, then U will act only as identity on A, meaning that overall we have a smaller circuit to learn, which only acts on the rest of the qubits. But of course, we cannot do that because we don't know what the blue gates are. So here is a basic idea. Since we don't know the blue gates, we can sort of guess a small circuit shown in the green to disentangle the region A. And then we can test if the qubits in A has indeed been disentangled, meaning that overall the circuit acts as an identity on A. Now, let me say it in a slightly more formal way. So we call this idea local inversion, which is to guess a small circuit to disentangle the region A. So how does it work? Well, because the green circuit is very small, we can actually enumerate all of them. And for each of them, we can test if the region A is indeed disentangled. So here is the key issue, which is the small circuit in green that we apply could be different from the actual light cone in blue. Because even though we can disentangle the region A, what we applied, which is the green gates, is not necessarily exactly canceling the blue gates. In other words, instead of removing gates from the unknown circuit, what we are actually doing is actually adding more gates on top of the circuit. And in this case, it really creates a mess on the remaining qubits. Next, let me show you the key idea to get around this issue, which is a three-step procedure: disentangle, swap, undo. And let me just show you how it works. Our starting point is the same picture, just more abstract, where we have this shallow circuit in red, and we have applied this local inversion V1 on top of it to disentangle a qubit A1. Because of the issue we just discussed, the circuit on the remaining qubits, U prime, could be a lot more complicated. But we will see that we can get around this issue by the following key idea: introduce a new ancilla qubit, swap with A1, and then undo V1. So let's see how it works. First, we will introduce a new ancilla qubit, B1. This is effectively not doing anything. And then we swap it with the qubit A1, which looks like this. And next, we will apply the inverse of the local inversion, V1 dagger, which looks like this. And notice that in this picture, we almost didn't do anything at all. Because indeed, if we didn't introduce this swap, then what we have done is just V1 dagger, which is literally nothing. But because of this swap, we sort of, in the final picture, have changed the role between A1 and B1. And therefore, effectively, the final picture looks like this, which is the same picture except that the input to the circuit has been changed to B1 instead of A1. So now, let's summarize what we have done. We have learned a small circuit, a unitary W1, acting on top of U such that it achieves the effect of swapping an input wire, which looks on like the right-hand side. And the key observation here is that instead of creating a mess, what we have is a very clean picture, where if we look at the right-hand side from the top, it feels like nothing has changed. And therefore, the system is not disturbed, and we can therefore repeat this procedure for every qubit. So now, the claim is that this idea actually works, and using this idea, we can learn the description of a 2n qubit circuit W that satisfies W equals U dagger tensor U. And this means that we have learned the circuit U because we can use W to implement it. So let's see why this is it. So we start with the same picture where W1 achieves the effect of swapping an input qubit. But now, since in the top picture, the system is not disturbed, we can repeat this procedure for every qubit. So if we do the same thing for every qubit, then effectively we have swapped every input qubit with a new ancilla qubit, which looks like this. This looks like a big mess, so we can swap everything again on top to achieve this. So let's sort of understand what we have done. We have essentially learned a 2n qubit circuit W that satisfies this picture. So we have the unknown shallow circuit U acting on A and n ancilla wires on B. And if we put W on top of it, it sort of achieves the effect of swapping the entire system A and B. So if we examine this picture, it indeed implies that W equals U dagger tensor U, which means that we have successfully reconstructed the unknown circuit U. To summarize the key idea, we basically achieve this by disentangling a local region without disturbing the system. Next, I will talk about how to reconstruct the circuit in low depths, meaning how to guarantee that the learned circuit W is shallow. So we will look at a 2D example, where we will show how to reconstruct the circuit in 3 steps. Our starting point is this interesting picture showing a 2D lattice, which is divided into 3 colors, green, red, and blue. This picture has the very interesting property that each small region that has the same color is far away from each other. For example, we can see that each green square is far away from the other squares, and the same for the red and blue. So here is what we do. Let's do this procedure in parallel for all green regions, where we first apply a local inversion operator. Notice that we can do this in parallel, indeed because all the green regions are far from each other. And then we swap the entire region, each of the entire green region with ancilla wires. So now you may be wondering, how do we implement this swap procedure? Because we don't want to connect with some very far away ancilla qubits. So now we use a sort of new trick, which is to implement this on this extended geometry, where we have these red ancilla qubits, and each of them is connected to the system qubit. So this guarantees that all the swap operations are local. And then we can simply undo the local inversion operators in parallel. And now we can repeat all of the above steps also for red and blue. And finally, we swap all the qubits with ancilla qubits. And this completes the reconstruction procedure in low depths. To wrap up, next we will show that there's actually a further simplification for the argument. So here is a key observation, which is if we examine the steps 1 to 3 in the previous page, they can actually be merged into one single step. So instead of using local inversions, we can actually consider implementing these operations U dagger SIU, where U is the unknown shallow circuit and SI is a swap gate between the ice qubit and the ice ancilla. So I will skip explaining why this is true, but it's actually very simple, and I will do one sanity check, which is to see that these operators U dagger SIU is indeed local. So here is the picture for U dagger SIU. We can have the shallow circuit U on the bottom and with the swap operation, and then the inverse of the shallow circuit U dagger on top. And we can see that all of the gates in U and U dagger cancel with each other, except for the blue gates, which is in the light cone of the ice qubit. This means that the operator U dagger SIU is indeed local. So now we will show that there is actually a simpler algorithm. So instead of learning local inversions, we can actually directly learn these local operators U dagger SIU and then combine them into a circuit that implements U tensor U dagger. So next I will explain the second half of the sentence, how to combine them into a circuit, which is via this simple identity which holds for any unitary U, where we have U tensor U dagger equals a product of swap operations times a product of U dagger SIU. And actually the proof of this identity is the same as our earlier picture of how to combine local inversions. But this identity is more general. It actually implies something stronger, which is that we can learn any unitary that maps a local operator to a local operator. So this family of unitaries is called quantum cellular automata, and they are more general than shallow quantum circuits. So this concludes our discussion for this algorithm. Next, we will discuss learning quantum states prepared by shallow circuits. So recall that we are given copies of an unknown quantum state psi that is prepared by some shallow circuit, and the goal is to learn a shallow circuit to prepare psi. So here, note that this is a very different problem, because here we only have access to the quantum state psi, not the quantum circuit that prepares it. So instead of having access to input-output samples, we only have measurement samples from the state psi. And we will see that the algorithm only needs single qubit random measurement samples, which is in the blue, which denotes measurement in random Pauli basis. So next, we will very briefly discuss this theorem, where we give a polynomial time algorithm for learning quantum states prepared by shallow circuits. And here we consider it's only on a 2D lattice from random measurement samples. So our starting point is the same basic idea, which is local inversion. Of course, here the local inversion has a different meaning, where applying it to the unknown state psi achieves the effect of disentangling some small region of qubits to the state 0 with some remaining unknown state phi. So what to do next? Well, here we have some similar issues, which is the remaining state phi could be a much more complicated state. Next, we will discuss the learning algorithm in 2D. The key idea is that to learn a 2D state, it actually suffices to solve a 1D constraint satisfaction problem, which is efficient to disentangle the states. So let's start with the left-hand side, where we have these small regions in blue, red, and green. So we can find many local inversions for each small region. But notice that the local inversions for the blue region will inevitably overlap with the local inversions for the red region. And similarly, local inversions for the red region will overlap with local inversions for both the green region and the blue region. But since these small systems are arranged in the 1D fashion, we can sort of solve a constraint satisfaction problem to choose one local inversion for each small region such that they are consistent, meaning that overlapping local inversions will share the same gates where they overlap. And in this way, we can sort of directly merge all of those local inversions into a shallow circuit that disentangles the entire region B. And now we can do these operations across the entire system, which is in the right-hand side, where we can learn 1D shallow circuits to disentangle each of these gray regions, B1, B2, up to B7. After this, we can sort of see that the remaining system is disentangled into these remaining white stripes, A1, A2, up to A8. So we only need to learn these remaining stripes. This is sort of non-trivial, but we show that they can indeed be learned individually because they have a 1D structure, which is easy to manage. However, notice that this argument does have the inherent barrier of being unable to go into higher dimensions because it relies on solving this 1D constraint satisfaction problem. In higher dimensions, these problems will be in 2 and higher dimensions, which is hard to solve. So, is there an efficient learning algorithm in higher dimensions? This was initially left as an open question, but recently it was solved in this new paper by me and Zeph called Learning Quantum States Prepared by Shallow Circuits in Polynomial Time, where we introduced some new ideas to combine local inversions without solving any constraint satisfaction problem. And that's the reason that it can work in higher dimensions. So check it out if you're interested. Finally, let's have some discussion. First, we remarked that the first algorithm for learning shallow quantum circuits actually works for arbitrary or even unknown geometry. Because if we recall the one-line proof, which is decompose U tensor U dagger into this product on the right-hand side, we can sort of see that for arbitrary or even unknown geometry, each item within the product on the right-hand side is always a local operator. And they can always be easily learned using standard techniques such as classical shadows, even if their support is unknown. That's why this first algorithm works for arbitrary or even unknown geometry. So next, we notice that using ancilla qubits is absolutely essential in the first algorithm for learning shallow quantum circuits. And it's actually a very interesting open question to study. Is it possible to reconstruct the circuit without using any ancilla qubits? Actually, we don't even know if it's possible for using less than exactly n ancilla qubits. Although, interestingly, the second algorithm we introduced for learning quantum states in 2D actually can use no ancilla qubits if we assume that the shallow circuit has a finite gate set. And we think that this argument probably works for learning shallow quantum circuits in 2D as well, although we didn't prove it. Finally, let's discuss the outlook towards useful quantum advantage with learning shallow quantum circuits in NISQ algorithms. So in this talk, we have discussed two new learning algorithms based on local inversion that probably works in simple and clean settings. And they are very different from gradient descent, which is what people do in practice. And the interesting question is, can this be the basis of new efficient learning algorithms in more general settings towards useful NISQ algorithms? And for this, we need to address more practical issues such as noise. So this talk is really the beginning. So, on that note, I hope you guys have enjoyed this video. If you are not already subscribed to the channel, make sure that you smash that subscribe button below, and we will be back soon with another great video. See you guys. Have a good one. Bye.